Okay, so let me post the link. Okay, so I just posted the link to the live stream in the chat. So welcome everybody. So it's why can't I share my okay, it's a little weird.
It pop up for us briefly. I'm not sure.
Yeah, it's not letting me share my whole window. Let me just see what's going on here. Okay, well, I guess I'll just share my whole screen. That's not optimal. Is this okay? Can everybody see? But wait, you can also see the Zoom toolbar, I guess? Or no? Okay, good. So maybe this is okay. Okay, so it's lecture 16. Oops, not sure what's going on with this. And I had said I was going to start doing probability, but I'm actually going to do one more lecture on counting. So in the traditional ordering of the course, there's another section on counting later. But as I was preparing the lecture, I realized that it doesn't. I don't really understand why it's later. I think we should do all of the counting at once. So one more lecture on counting, and this lecture is on so-called advanced counting techniques. And this is the content of chapter 8, section 1, and 8.5 to 8.6. But before I get to that, I want to make 2 remarks on the counting that we've already done, just to clarify some notion of what it means to be distinguishable, since many people have been asking about this. So here's one remark. So let's consider 2 situations. Let's consider one situation where we put 3 distinguishable objects, which are going to be labeled tokens, into 2 boxes. Okay, so you have n equals 3, and this is the case where the objects are labeled, which is another way of saying that they're distinguishable. Okay. And in this case, so I'm putting 3 objects into 2 boxes. And in this case, we've discussed that the number of ways to do this is k to the n. And the reason for that is that there's a sequence of choices for specifying such an allocation. And the sequence of choices is simply, you look at the first object and you decide, well, does it go into the first box or does it go into the second box? And then you look at the second object and you decide, well, does it go into the first box or the second box? And the key point here is that different choices in this process correspond to different allocations, because if you put the first object in the first box and the second object in the second box, that's not the same thing as if you put the second object in the first box and the first object in the second box, because they're labeled. Now, let's contrast this with the situation where you have, again, 3 objects, but they're unlabeled. So they're just tokens. So this is indistinguishable. slash unlabeled. So you can't tell them apart. And again, you're putting them into two boxes. And again, you could ask, well, let's specify an allocation using choices. So you could try using the same choices, that you decide whether the first token goes into the first or the second, and then you decide if the second token goes into the first or the second. But now these are two different ways of making choices, but they both lead to the same allocation, right? If you make the dotted line choices, you get the same allocation as if you make the undotted line choices. So here you have the different choices correspond to the same allocation. And here you have the different choices correspond to different allocations. And that's why you can't use the same choices to count the number of allocations on the right-hand side. And that's why you have to do something else, which is, all this stuff about bit strings and whatnot. And you finally get the answer is that the number of ways is n plus k minus 1, choose k minus 1, which is different. So any questions or comments about that? So this is different from this. Okay, so that's one remark. The second remark I want to make is on a question which was asked a couple of lectures ago. I mean, the second remark is really a whole theorem in its own right. And the remark is, let's now consider, in the binomial theorem, we had x plus y to the n. What happens if we take x plus y plus z to the n? In other words, what happens if we look at an n-wise product of this expression, x plus y plus z, where x, y, and z are variables, like, in algebra, just as we usually have. Now we can ask a number of questions. So one question is, how many terms are there before grouping? If you expand this out, you distribute all of the products. How many terms will you get? So let's think about this for a moment. And I want you to use your counting methods. What is a process that specifies a term?
First, choose the x, y, or z from our first factor. Then choose x, y, or z from our second factor, etc., until we reach x, y, or z from our nth factor.
That's right. So number of terms before grouping is just number of choices for the first factor let's call this F1. So let's give these names. I don't know why all these things have become much thicker, but okay. So this is F1, this is F2, this is all the way to Fn, times the number of choices for F2, all the way up to number of choices for Fn. And for each one, there, you can choose one of three terms. So this is 3 to the n. Now, what about the total number of terms? Total number of terms after grouping. So what that means is, if you have terms with the same powers of x, y, and z, you just combine them into one term by adding them and making a coefficient. So this is this means number of distinct words of length n in x, y, and z, where the order doesn't matter. Okay. So any thoughts on how to solve this problem?
It looks like we're putting n undistinguishable objects into 3 boxes, because we know that for each of them, their total power has to add up to n.
Yeah, exactly. So this is the number of ways to put n tokens corresponding to the factors into 3 boxes corresponding to x, y, and z, which we know is n plus 3 minus 1, choose 2. So it's n plus 2, choose 2. So this is different from what we had in the binomial theorem, right? In the binomial theorem, we had n plus 1 terms, which is actually n plus 1, choose 1. Now you have n plus 2, choose 2 terms. So when you when you group the terms, the number goes down a lot. And finally, you can even ask yourself, what is the coefficient? So what is the number of times the term x to the n1, y to the n2, z to the n3 appears? And of course, the sum of these numbers has to be equal to n. Is what? So does somebody else have a thought about this? It's again a counting problem. How do you set this up as one of the counting problems that we know? So what are we trying to count here? The number of terms before grouping. So terms before grouping are words of length n where order does matter, right? So just to make it clear. In this case, is order doesn't matter. So now, yeah, how many words where the order does matter correspond to a choice of frequencies of x, y, and z?
Would it be something along the lines of like n factorial over and then the factorials of each of them, because you could rearrange them in some number of ways that's related to the factorial
Yeah.
of how many there are?
Yeah. So you can solve this using either your permutations with repetitions calculation, or this calculation of putting distinguishable objects into boxes when you have some constraints on the number, but you get this. Okay. So actually this question combines many of the counting techniques that we discussed. So the answer is, finally the answer is this, right? If you expand this out, this is what the coefficient of x to the n1, y to the n2, z to the n3 is going to be. And this is the generalization of the binomial theorem to 3 terms. And you can do it to any number of terms, but this is the idea. So any comments about this? Okay. So let's move on to the so-called advanced counting techniques. And there are going to be 2 motivating examples. So example 1 is how many words in the letters L and A are there of length 100 such that no two L's are adjacent. Okay, so this is like la 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 la. It's like expressions like that, but you're not allowed to have two L's. Okay, so this, I don't know a way to easily solve this using the other techniques. I mean, maybe you can combine them, but it's not so, it really doesn't fall immediately into any of the things we've looked at. So that's one example. Okay. And then the second example is a classic example in combinatorics called, well, I'll just pose it a little differently. So suppose there are 260 ticketed passengers on a flight with assigned seats. Okay, so ticketed just means with assigned seats. Maybe that's not the best word. So every passenger has a seat. So it's not Southwest Airlines. How many ways are there for them to sit down so nobody sits in their assigned seat? Such that no passenger sits in their assigned seat. Okay, so these are the two motivating questions. And now we'll explain two techniques for solving them. The first technique is called recurrence relations. And the second technique is called inclusion-exclusion. Okay, and this is roughly 8.1, and this is roughly 8.5 and 6. So any questions about these two statements? So the constraint here is no passenger sits in their assigned seat.
Could you explain the example one again?
So example one is, I have words like, okay, word 100 is a bit long, so words like LA, LA are allowed, AA, AL is allowed, but AA, LL is not allowed. You can't have two L's next to each other.
Oh, got it.
Yep.
And for the first approach, it's called recurrence
relations. Yeah, recurrence. Okay, so recurrence is actually just another word for recursive definition. Okay. So so recurrence, it's not a new concept. It's just the same concept you've seen earlier in a different context. A recurrence relation is simply a recursive definition of a sequence. A0, A1, A2, etc., etc. What that means is it defines AN in terms of the previous ones, as you are now well versed with doing. Now, what does this have to do with solving example one? So let's see that. Let me copy example one over. So here's example one. So what's the idea here? Well, I'm going to define a sequence. So right now, this problem is given to me for bit strings of length 100, right? So there's a number given here. But what I'm going to do is I am going to consider this problem for bit strings of any length, right? So let an be the number of such words of length n. So I've introduced this new variable n, which is the length of the sequence. So okay, so what's A1? That's the number of such words of length 1. How many words are there of length 1?
Two words.
2, yeah, just A or L, right? How many words are there of length 2? So there's AA,
3.
AL,
So it's 2
LA.
to the n.
Well, it doesn't look like 2 to the n, right? Because this is 3 now. You can't have LL, remember? Right?
Oh, I thought
No
it's
two
like
L's are adjacent. So
all
such means
possibilities.
no two L's are adjacent. Okay. So it's not 2 to the n. Now you could keep doing this, but the key observation is that to construct a word of length n, you can write down the choices in a way that you can reduce it to constructing words of shorter length. Okay, so let's do it this way. So consider the following process for constructing a word of length n. So the first step is well, or you know what? I actually, yeah, okay. Okay. Let's see. How do I want to say this? Okay, it's a little verbose, but I'll say it this way. So let the first letter be A. So you have A. And now you have n-1 remaining letters to go. And what can you put over there? Well, you can put any other word in which no two L's are adjacent. Right? Because the first A does not put any constraint on what that word can be because it doesn't have any L's in it. And now choose a word of length n-1. Or there's a second option. The second option, the first letter is an L. Okay. But if the first letter is an L, what does the second letter have to be?
It must be A.
It must be A because you can't have LL. So you have LA, and now you choose the remaining n-2 letters, however you want, because there's an A in front of it, right? Or let the first 2 letters be LA, and now choose a word of length n minus 2. Okay, so this defines a process. It's like you either do this or you do that. You're in one of these two cases. And now the point is that this process can be used to uniquely specify words of this type. Right? So the key thing is that these two are mutually exclusive. So it's one or the other. And that's all the words. Right? There are no other words. Every word begins with either A or L. And so these are the only types of words. And so by the sum rule, an is equal to the sum of the number of ways to do each of these choices. But now, how many ways are there to do the if you're in the first case, how many ways are there to choose a word of length n minus 1?
A sub n minus 1.
A sub n minus 1, right? Yeah. A sub n minus 1 ways, and this is A sub n minus 2 ways. And so by the sum rule, the total number of ways is an is equal to A sub n minus 1 plus A sub n minus 2. And this actually is a solution of the counting problem. Right? Because I've recursively defined this function A sub n. This is the base case. And this is the recursive step. And now if I have these, then I can compute A of 100 relatively quickly. I mean, not that quickly. I have to do 100 little arithmetic operations, but that's a lot faster than listing all the words. Right? So this is a recursive, so this is a recurrence, and this is an implicit solution of the counting problem, right? So what does that mean? It means it's not exactly a formula, but you can use it to efficiently compute these numbers. Okay. So this is one form of a solution to this problem. And we can step back and make a philosophical point here, which is anyway, the counting formulas we've been producing, we never actually do the arithmetic and write out the number, right? Even those are somewhat implicit. They're saying, hey, this number is a product of all these numbers. In this case, you're kind of saying, hey, look, it's a sum, it's given by this recursive definition. So any questions or comments about this?
So for the first two steps, when you let the first letter and the first two letters be A and LA, how can you assure like for the rest you don't have like two L like next to each other?
Right. Yeah. So that's the beauty of the recursive step, right? This n minus 2. So by word, I mean a word without two L's, right? So it's already built into this. It's taken care of by the recursion. So what by word here, I mean without two L's, right? Without LL. So that's what guarantees it, because in the definition itself, I'm saying I'm never going to do LL.
So it's like an assumption.
No, it's not an assumption. It's a recursive definition, because that's the beauty of recursion. I'm already assuming A sub n minus 1 is the number of such words of length n minus 1 without LL. And so what this is saying is that the set of words of length n without LL are in bijection with the union of the set of words n minus 1 without LL and the set of n minus 2 without LL. So it's expressing the answer to the
Oh.
n length problem in terms of the answers to smaller problems. So you're right, it's not giving me a formula, right? But it's expressing the answer to the bigger problem in terms of answers to the smaller ones. Does that answer the question?
Yeah, but we still don't know like the actual number of step 1 or step 2, right?
No, but if I asked you, right? So this is what I'm getting at. This is what it means by what does it mean to know the answer, right? So I claim that this is actually, in a way, knowing the answer, because if you plug this into a computer, it could very quickly tell you the number, right? I mean, in a way, this is a program for outputting AN. It's saying that you start with 2 and 3, you know, and you generate the sequence, right? So you have 2, 3, 5, 8, 13, et cetera, right? And I mean, it's not an explicit formula, but it's pretty good. It can be used to efficiently compute the number.
Got it.
Yep. So by the way, this is actually the same, almost the same as the Fibonacci numbers, right? If you ignore the first 2 numbers, this is the same as the Fibonacci numbers.
Would this actually calculate faster than like choose something out of 100 formula?
Yeah, it would, because as I mentioned earlier, even the way you would actually compute these binomial coefficients on a computer is with a recursive formula anyway. So this is kind of just giving you the formula. Okay, let's do another example. Or any more questions about this? Okay. Let's do another example. Okay. This one's a little bit of a mouthful to state, but here it is. So so suppose we have n variables, or suppose we have 5 variables: x0, x1, or I guess in this case 6 variables. So given this product, how many different orders are there to multiply these variables? So in other words, how many different ways are there to parenthesize? So actually, maybe for simplicity, let me just do it with 3 variables, actually, right? So what do I mean by ways to parenthesize? Well, okay, it's more interesting if you do 4 variables. So I have to multiply out these 4 numbers, right? So I could first multiply. So I could multiply the first 2. Sorry. And then I could multiply out the next 2. That's one way. Or I could, so I could multiply out the last 2. Then I could multiply that product by x1, and then I could multiply the whole thing by x0. Or I could do it the other way. I could multiply out x0 by x1. So I'm not allowed to rearrange the letters. Maybe that's the key here. I have to keep the order of the variables the same, but I'm allowed to put parentheses wherever I want. And then I multiply these by x2. And then I multiply this by x3. Anybody see any other ways to do it? Well, I mean, okay, I could also do this. I could multiply x1 by x2 and then multiply both of those by x0 and x3 like this. So I'm trying to count the number of ways to do that. And the question is, how many ways are there to do it for n variables? So it seems like a difficult question. N plus 1 actually turns out to be more convenient. Okay. And I'm not allowed to put parentheses around the whole thing. That's considered redundant. Now this comes up a lot, actually, weirdly, in math. It's in bijection with a lot of other interesting counting problems. And there's a very slick way to solve this using recurrence. So let Cn be the number of ways to parenthesize n plus 1 variables. So this is n plus 1 variables, right? It's the number of ways to place parentheses that are grammatically correct is basically what it's asking. So, okay, so C1 is just 1. Okay. And now the key observation is that suppose you want to parenthesize n plus 1 variables, right? Here's the process. So let's see, let me make sure I have this right. I'm not sure I want to allow 3. Let me just check this for a moment. Okay, good. Yeah, I need one more constraint here. So the constraint is that that every product should only have 2 terms in it. I'm not going to allow 3 wise products. So I'm actually going to insist on this. Okay. So I'm viewing multiplication as an operation on only 2 variables at a time. So how many ways are there to put parentheses? How many ways are there to compute this product by multiplying pairs of quantities? Okay, so good. So to construct a parenthesization of n plus 1 variables, here's one way to do it. So choose one of the n dots okay, to be the outermost multiplication. So that means your expression is going to look like so let pi be a symbol for the parenthesization. I'm going to write it as some pi1 parentheses times pi2. Okay, so in each of the above examples, I can actually do this. I guess, okay. Okay, it's a little bit annoying because I haven't put parentheses here.
If we make it the innermost, can't we just use the product rule? Like, so if we make it the innermost and then we just treat like that new term as a single variable.
That doesn't work because there's no unique innermost.
Oh,
Like when you have very long strings, you can have many innermost parenthesization. So you have to do the outermost. So actually, let's just say you write it as pi equals pi1 times pi2. I'm not going to put parentheses there. Okay, so any such expression after you put the parentheses is going to be a product of two things, each of which is a parenthesized expression. Okay, so choose one of these to be the outermost parenthesization. And now, of course, the number of symbols in these things can be different, right? Depending on where you choose this dot. Okay, so assume pi has so when you do this, you're going to partition the symbols into two sets. So assume pi1 has k plus 1 variables, and assume pi2 has n minus k variables. Okay. Okay, so once you've done this, how are you going to choose the rest of the parenthesization?
You will choose a parenthesization for each part, the pi1 and
Exactly,
pi2.
yeah. So choose a parenthesization of pi1 and then choose a parenthesization of pi2. And now how many ways are there to do each of these steps? How many ways are there to choose a parenthesization of pi1?
C sub k plus 1.
C sub k. So C sub n is the number of ways to parenthesize n plus 1. So this will be C sub k ways. And this will be C sub n minus k minus 1 ways. Okay. And so now, by the sum rule, so of course, okay, so the number of ways to do step 2 depends on how you do step 1, right? In general. And so so by the sum rule, the total number of ways, you have that Cn is equal to C1 times C n minus 1 sorry, I have this wrong, Cn minus 2 plus C2 times Cn minus 3 plus C4 times Cn minus 5 all the way up to Cn minus 2 C1. And so this is also a valid recursive definition of these numbers. This is sometimes written this way: summation k goes from actually, sorry, I guess you can go from 0 in this case. So I missed a term. Yeah, okay, so maybe I should add a base case. C0 is also 1. And if you write this out, you get this recursive definition. So k goes from 0 to n minus 1 of ck c sub n minus k minus 1. And the key is that all the terms on the right are ck's for k strictly less than n. So this is a valid recursive definition. So this is a very important sequence. It's called the Catalan numbers. But I mean, okay, admittedly, this is a quite complicated example, and I'm sorry I didn't do a very good job explaining it. But the basic idea is the same. It's that I found a way of expressing the number of objects of size n plus 1 in terms of the numbers of objects of size smaller. And the key to that was to observe that to construct such an object, I can do it recursively. Okay, so any comments or questions about this? Sorry to mess that up a little bit.
Yeah, I have a question.
Mhm.
I'm wondering about one of the other possible ways. Is it kind of restricted to like 2 or more kinds of parentheses? For instance, could you do like x not on the outside and then the other set of parentheses, envelope x1, x2, x3? So you have like 2 pairs of parentheses. Like, is that valid or no?
Sorry. So are you talking about so you have x0, x1, x2, x3, and where do you want to put the parentheses?
Is it possible to just put one pair on x naught just by itself and then
Like this?
yeah, and then like the others, which I guess is just saying multiply the others against like x1, x2, x3, just multiplied together.
Yeah, absolutely, and that's included here. See, that's so I'm not putting parentheses on one variable since it's redundant, but that's the same as this.
So multiplying x naught times and then in parentheses x1 times x2 times x3, which would be like technically I guess x naught wouldn't necessarily need a parentheses at that point.
Yeah.
That's actually seen as the same as saying x naught times in parentheses x1.
Yeah, okay.
Times x3.
I see your point. I see your point. So we have to add a convention here, which is that single variables cannot be parenthesized. So it's a good point. Whenever we set up a counting problem, everything should be precisely defined. And I think part of the reason I messed up this exposition is that I didn't begin by very precisely describing what even we're counting. And so, okay, what we're counting is you're allowed to put parentheses around products. You're not allowed to put parentheses. So it's really a recursive definition of a set that you're allowed to multiply 2 parenthesized expressions. So a parenthesized expression is a product of parenthesized expressions. That's the recursive definition. And the base case is just single variables. So anything you can generate by starting out with single variables and multiplying them and putting parentheses around expressions that involve more than one variable, that's a valid parenthesized expression. So just to close the loop on this, I came up with this formula. Let's figure out what C3 is, right? That's what was our original problem. C3. What's C3? So let's figure out what C3 is. So C2 is C1, C1. Sorry, I have it wrong. It's C0. Yeah, it's just C1, C1. Right, because K goes from 0 to 1. Okay, sorry. If I mess this up again. Sorry. C2 is C0, C1 plus C1, C0. And C0, C1 is 1 plus 1, which is 2. And this is correct because C2 is counting the number of ways to parenthesize x0, x1, x2. And there are only 2 ways to parenthesize that, this and this. Okay. But now let's get to C3. So let me, so C3 is going to be C0, C2 plus C1, C1 plus C2, C0, which is 1 times 2 plus 1 times 1 plus 2 times 1, which is 5. And so indeed, we have 5. I missed the last one. So we have 1, 2, 3, 4. And the last one is the one where you put the parentheses like this. So that's indeed 5 different ways. So this formula that we derived works. Okay, so I hope that example at least explains what's going on in the proof a little better. Since this was a little bit murky, I would encourage you, so this is in the book. This is example 5 in the book. If you're confused about this, so read example 5 in the book. Okay. Any more questions or comments about this? So again, there's a recursive step and a base case, right? This is the recursive step. And this is the base case. So this is a method of counting which actually allows you to solve this problem, right? In the end, we were able to solve the problem, but it does it in a way that's kind of based on induction rather than the counting rules.
Yeah, I do have another question.
Mhm.
So with the base case, I'm assuming like C0 would refer to like having one total term. I'm
Exactly.
assuming,
Yeah. Exactly.
C1 is having 2 total terms. It would be like X0 and X1.
Exactly. So let's just draw out the base cases here. So C0 is the case just X0. There's only one. There's no. You can't put parentheses. So that's it. And C1 is X0 times X1. And you're not allowed to put parentheses on the whole expression either. So there's only one way to do that. So the whole expression should not be parenthesized.
Yeah, I was
Okay.
gonna bring up that part there,
Yeah.
but the whole expression not being able to
Yeah.
earlier.
So you're right. I should have specified where are you allowed to put parentheses. So you're not allowed to put parentheses anywhere where it's redundant. So you're not allowed to put around one variable or around the whole expression because that doesn't achieve anything. It's not actually grouping a multiplication. So this point is important. And once you do this, then the problem is well defined. And then indeed, these are the base cases. They're both 1. And then indeed, you know, this proof works out. So the key point is that every parenthesized expression has an outermost multiplication. That's what we used here. But yeah, you had a question?
Is there some limit to how complicated these implicit answers can be?
That's a great question. So the more complicated they are, the less useful they are. So this one, is not as nice as the previous one. As you saw, it's a little bit harder to compute. So really, the way to think about it is that in math, there's a range of explicitness with how you specify quantities. The most explicit, you just write it down, or you have a formula. But even the simplest formula involves some computation, right? Like even the binomial theorem involves some computation. So you should really think of it as a spectrum. And this is less explicit than the previous one.
Thank you.
Okay, so I want to make one remark, which is that what I've taught you, what I've told you about so far is how to find a recursive definition of the answer. So how to find a recurrence satisfied by the answer, right? And that's an implicit description. There are methods to get an explicit formula from the recurrence. Okay, so the process of obtaining explicit formulas or an explicit formula from an implicit recurrence is called solving the recurrence. Okay, so in general, in totally general, there's no algorithm for doing this. It could be complicated. But I mean, okay, so for example, you have the Fibonacci numbers, right? F naught equals 0, F1 equals 1, Fn equals Fn minus 1 plus Fn minus 2. This is an implicit description of the Fibonacci numbers. Now, it turns out you can actually solve this. I won't explain how. This is done in chapter 6.2. And you can get a formula, namely Fn is equal to 1 over square root 5, 1 plus square root 5 over 2 over to the n minus 1 over square root 5, 1 minus square root 5 over 2 to the n. This is explicit. They both describe the same object, but one, I mean, even the right-hand side is not that explicit, right? If I ask you to compute that for n equals 100, you're going to have fun taking exponents of those numbers, right? So really, there are two different representations of the same sequence of numbers. Now, the art of solving recurrences is more a matter of like math 54 or math 185. And I don't want, it's not really about counting, so I don't want to stress it in this course. So so if you want to learn how to solve very simple recurrences, in chapter 8.2, read theorems 1 and 2. Don't read the rest. In my opinion, it's a mess. It's kind of ad hoc. So how to solve very simple recurrences. And this is optional. But if you're curious, you can read about it in section 8.2. I'm not covering it in this course. If you really want to learn how to do it in detail, take math 54 or math 185. And the key word, if you took math 54 with me, is diagonalization, which, as you all know, is my favorite thing. That's how you solve recurrences. Okay, so that's all I want to say about recurrences and recursive definitions for solving these counting problems. So any more questions or comments about that? And by the way, this Fibonacci example, this is example number 2 in section 8.2, if you want to read about it in detail. Okay, so now I want to move to inclusion-exclusion, which is a very interesting subject. And this is going to be used to solve the second problem. How many ways are there for these passengers to sit on a plane so that nobody sits in their own seat? Now, before I solve that problem, let me tell you the general principle. So recall that if you have A and B finite sets, then the cardinality of A union B is the cardinality of A plus the cardinality of B minus the cardinality of the intersection. I suppose we all know this fact by now. But let's ask what happens when you have three sets. Okay, so let's say you have three sets, three finite sets, A, B, and C. Let's draw a Venn diagram. Okay, now they're all finite. I want to count the total number of elements in A union B union C. And I want a formula for that in terms of some simpler quantities. So the key observation is that there are three kinds of elements in A union B union C. Right. So first, there are elements, which I'm going to denote by squares, which appear only in one of the sets. So square elements appears in one set. Okay, those are easy to count. The number of squares is just the sum of the squares in A and the squares in B and the squares in C. And then there are some more complicated elements, which are triangles, which appear in exactly two sets. And then there's some very special elements, so I'm going to call circles, which appear in all the sets. Okay. So now I claim that the following is a formula for A union B union C. And I'm going to prove it by looking at this particular stratification into sets. So cardinality of A union B union C is the sum of the cardinalities minus the cardinalities of the differences of of the intersections of pairs. Or let me do it this way. Plus the intersection of all three of them. Okay, now what's the proof? What's the proof of this? Well, I'm going to look at each of the three kinds of elements and count how many times they appear on both sides and with what sign. So let me actually move this below since I'm going to talk about this. Okay, so these square elements, these square elements, these, so how many times do they appear on the left-hand side? And how many times do they appear on the right-hand side? On the left-hand side, every element appears once. It's just A union B union C, every element appears once. On the right-hand side, in which terms do the squares appear?
Only the first three.
Yeah, each square appears in exactly one of these terms. I mean, okay, I don't know if that's a very good depiction of it. Maybe "or" is not the right word, but each square appears in exactly one of the first three terms. So it appears exactly once on the right-hand side. Okay, now let's look at the triangles. Well, each triangle appears once on the left-hand side because it's an element of the union. But now how many times does the triangle appear on the right-hand side? Well, it appears in 2 of the sets. So triangle appears in 2 of these first terms. Or maybe I'll use color coding to make this clear. So let's look at this triangle. So it appears in A and C, but not in A, B, and C, right? Well, it's going to appear in A with a +1. It's going to appear in C with a +1. And it's going to appear in C intersect A with a -1. And it's not going to appear anywhere else. So these triangle terms appear 1, +1, -1 times in the right-hand side, which is also 1. And finally, the circle, where how many times is that going to appear? Well, that appears everywhere, right? It appears in every single term on the right-hand side. So on the left-hand side, it appears once. And the circle is in A, it's in B, it's in C, it's in all of the intersections, and it's in the triple intersection as well. So it's going to appear 3, -3, +1 times on the right-hand side, which is also 1. So it's a conclusion, well, each term appears the same number of sides, same number of times in both cardinality, in both sides, right? So each term is counted the same number of times on both sides. So this formula, let's call this formula star. So star holds. So that's inclusion, exclusion for 3 sets. So any questions, comments about that? This is the generalization of this formula that you've been seeing earlier, the 3 sets. Okay, so there's a general theorem, which I will now state for K sets. So the general theorem says if you have a bunch of finite sets, A1 through AN, then the cardinality of the union of all of them behaves kind of the same way. Okay, so looking at these 2 examples, what's the pattern? What's the pattern in this formula?
The sign switch each time you add an additional like length to the union.
Yeah, so the way to interpret this is, first you just add up A, B, and C, but then you double counted the elements that appeared in 2 sets. So you removed them. But then you removed the elements appeared in all of the sets twice. So you add them back. So you have this alternating sign pattern. And the general principle is the same. It's called inclusion, exclusion. So this is the sum of the cardinalities of all the sets. But then you subtract the pairwise differences. So this is all pairs. And then you add all the triple intersections. And then you keep repeating this until finally you get a -1 to the n, -1 times the intersection of all of them. So that's the theorem. It's that's why it's inclusion exclusion, because you include some things, then you overcount it, so you exclude some things, but then you undercount it, so you include some more things, that you overcount it. If you keep doing this, you get the right answer. And there's a succinct way to write this in summation notation, which I will write now. Or okay, I don't have to write those words, I suppose. I'll just write it out. This is equal to summation as k goes from 0 to n, minus 1 to the k minus 1. And now we're going to do something that's a little bit, it might be a little bit uncomfortable the first time since we haven't done this before. I'm going to sum over all subsets of 1 through n of size k. Okay, so this notation means I'm going to add up some quantity over all subsets of size k contained in the set 1 through n. And the quantity I'm going to add is the cardinality of the intersection of AIs for all i's contained in that set. So this is the inclusion exclusion formula. For general intersection of, for general union of n sets. Okay, so what do these terms mean? This means summation over S with, with these properties. And this notation here, this means, it just means intersection of AI for all I and S. So this is a, I mean, yeah, I guess this notation was introduced in chapter 2, so I don't have to introduce it again. So any questions about the statement? Okay, so, I mean, let's see. So I'm running out of time, so I was going to do an example and a proof. Do people have a preference? Should I do the proof of this or an example?
Example.
You can just enter in the chat. Okay, example, proof, example. Okay, it looks like more people want example. So let's do an example. So there are two ways to prove this. The proof is in the book. It generalizes what I just did, actually. It's actually the same as what I did. So proof number 1 is induction. Proof number 2 is generalize the above, namely count the number of times an element which appears in R sets is counted on each side. And you can just read this in 8.5. But let me show you, let me now get to our motivating example of these people on flights that we wanted to answer, right? So we go back all the way to the beginning. We have the situation where we have 260 passengers. Oh, whoops, what just happened? Yeah. Okay, let's solve this example. Okay, so first of all, let's formalize this into a mathematical quantity. So so this actually has a name. It comes up a lot. So a permutation, let's call it pi 1, pi 2, all the way up to pi n of 1 through n is called a derangement if no number gets mapped to its position. So if pi I is not equal to I for every I in this set. Okay. So this seating arrangements with this property are just derangements. Because what are you doing? Well, you have passengers 1 through 260. Each of them was originally assigned to their number. And now you want to permute them in a way so that the ith person does not get assigned to the ith number. So this is just a derangement. So this quantity is equal to the number of derangements with n equals 260. It's a number of permutations of 260 elements such that no element gets mapped to itself. Okay, so we're going to use inclusion, exclusion to count this. So, well, I'm going to do a little trick first. So let A sub 1 be the set of permutations such that pi has exactly one fixed point. So here's another definition. An index I in the set such that pi I equals I is called a fixed point. And so A1 is going to be the set of permutations with exactly one fixed point. And in general, AR is going to be the set of permutations with exactly R fixed points. Sorry. What am I saying? Not exactly R. It has sorry, I set this up wrong. Sorry, this is not easy to count. So I'm going to say let A1 be the set of pi so that 1 is a fixed point of pi. So just pi 1 equals 1. And in general, AI, let's call it, is just a set of permutations such that I is a fixed point. All the way up to AN. Okay, so now the number of derangements is so by the way, do any of these AIs contain any derangements? No, by definition, they all have at least one fixed point, so they don't contain any derangements. But now what if I have a permutation that's not in any of these sets?
That it is a derangement.
It's a derangement, right? The number of derangements is n factorial, that's the total number of permutations, minus the cardinality of the union of all of these sets. right? So because this is all permutations, and this is permutations with at least one fixed point, right? Because if you have a fixed point, then one of the indices has to be a fixed point. And so if I can estimate the second cardinality, I'm done. So let's do that. Let's apply inclusion-exclusion. So by inclusion-exclusion, the cardinality of this set is this, right? Summation k goes from 0 to n minus 1 to the k minus 1 times the summation over all subsets of 1 through n of size k of this cardinality. So now, in order to use the formula, I need to estimate what these cardinalities are. And so let's fix a set S. Can somebody describe in words what this set is? This intersection?
It is the permutation with all the like say S was 1, 2, 3, it would be the permutation with 1, 2, and 3 as fixed points.
Exactly. So by definition, that this set, this is the set of permutations such that pi I equals I for every I in S. And so this is permutations with a certain number of fixed points. And how do you choose a permutation where certain indices are fixed? So let's say, you know, I'm gonna cross out these fixed indices. So for example, if the S has 3 elements, then these are fixed. Then how do I choose a permutation on the rest of the well, okay. I guess at this point I've really run out of time, so I think I'm just going to continue this next time. Sorry, but you can ponder this. Okay.
It's just like n minus k factorial.
Yeah, it's actually just it's just n minus cardinality of S factorial. That's right. But I want to do it well, so I'll do it next time. But that's absolutely right.
Is that like a common method?
What, this calculation?
I mean, n factorial minus the